In this video here, we're going to take a look at adding and subtracting volumes. Now, to solve more complicated volumes of revolution problems, we may sometimes have to add or subtract volumes. Now, as you work through problems based on adding and subtracting volumes, you may find the following formulae helpful here. So what do we have then? Well, for a cylinder with radius r and height h here, this will have volume of pi r squared h. Very much a result that you should be familiar with. Then we also have a cone here with base radius r and height h, and this will have volume of 1 over 3 pi r squared h. And again, this is very much a result that you should be familiar with. So a very quick introduction there to adding and subtracting volumes, but we don't really need too much more. I think the best way to demonstrate this then is to take a look at one practice question. So let's get started then with this practice question here. Let's take a look then at this example here for adding and subtracting volumes. So what do we have for this question here? Well, what I can see straight away is we have this diagram here. And this diagram shows the shaded region R, which we can see here, which is bounded by the curves with these given equations here. So for my first equation then, we have y equals 2 root x. That's this curve here then. So let's just denote this here, y equals 2 root x. We also have y equals 1 over 4x. That's this curve here at the bottom. Y is equal to 1 over 4x. And we also have the line x equals 1 here. So that's this dotted line here, right? So the question then says that the region is rotated 2 pi radians about the x-axis, and it then asks us to show that the exact volume of the solid generated is 27 pi over 16 here. So where do we begin then? Well, let me do this in orange here just to highlight this. So when I look at this diagram here, I see straight away that if I find the volume then underneath this curve between this point here, which we don't know, we'll just call it A, and this point here 1, then what that would give me here is this volume in orange, right? Now for this question, what we're actually looking for here is the volume of the shaded region R. So what I want then is just this region R, right? This blue region here, but I've got this part underneath this curve here, this volume that I don't actually want. So if I think about this now as two separate volumes then, so the volume underneath this curve here then, y equals 1 over 4x, we'll call that V2. And then the full volume here, let's call that V1. So again, I'll do that in orange here. We'll call that V1 here. And in that case then, the volume of the shaded region R here, we'll call that V subscript R. That is equal to V1 minus V2, right? If we do this difference here, that just leaves me then with the shaded region R, the volume of the shaded region R. So before we can find any volumes here, we also need to find this x coordinate here for A. So to do that, we need the point of intersection here for these two curves, right? So for the point of intersection then. So for the point of intersection here, that is equal then to, we get 2 root x is equal to 1 over 4x. So 2 root x is equal to 1 over 4x. Like so. So there's a few different ways you can go about solving this here for x. Completely up to you. What I'll do here is I'll divide both sides by 2. So if I do that then, I get root x is equal then to 1 over ax. Like so. And then if I times both sides by x here, what would I get then? I'd get x to the power of 3 over 2 on the left-hand side. X to the power of 3 over 2 on the left-hand side. And then on the right-hand side here, we just get left with 1 over 8. Like so. And then finally here, if we just want x then, if I just raise both sides then to the power of 2 over 3, we get x equals 1 over 8 to the power then of 2 over 3. And if we evaluate this here then, well, the cube root of 8 is 2. Square that, we get 4. So I get 1 over 4 there. Okay. So this point here then, A, well, we can replace that now with 1 over 4. Okay. So this point here then is 1 over 4. And what that gives me then is the limits here to any of our integrals here. Okay. So let's start then by finding this first volume here, V1. So let me do that in the same color here then, just so you can see how this matches up. So for V1 here then, in fact, let me do it underneath here just so I've got a little bit more room. So for V1 here then, this will be equal to pi times by the integral then. So the integral here then, and don't forget our limits here are 1 over 4 and 1. We get 1 over 4 and 1. Now, because we're going about the x-axis here then, we now integrate y squared here with respect to x. Okay, so we've got y squared with respect to x here. We've got y squared dx here. So y squared in this case then. So don't forget for v1, we're integrating underneath this curve here then. So this curve is y equals 2 root x. So what I get then is pi times by the integral then. Again, from 1 over 4 to 1. I do appreciate it is a little bit tedious inputting the limits each and every time, but it is important, of 2 root x all squared, like so. And this here then is with respect to x, so dx there. Okay. Well, 2 root x squared, so 2 squared is 4, root x squared is x, so we get 4x there as the integrand. We're integrating here then. Oops, I forgot my pi. I knew I'd make that mistake somewhere. Let's just get rid of that. Input the pi again. We've got pi times by the integral then from 1 over 4 to 1. So what I've got then, as we mentioned, is 4x with respect to x here. So 4x with respect to x. And this integral here then, nice and straightforward, just basic A-level maths integration. So what we get here then is pi times by. All we need to do then is add 1 to the power, divide by the new power. So we get 4x squared over 2, so that would give me 2x squared there. We get 2x squared there. And for the limits here, then we get 1 over 4 and 1. Okay. So all we need to do then is substitute our limits in. Don't forget we start with the upper limit and subtract the lower limit here. So we get pi times by here. So 2 lots of 1 squared, so that would be 2. Minus them. So 2 lots of 1 over 4 squared. So 1 over 4 squared would be 1 over 16. So 2 times 1 over 16, that would give me 1 over 8. I get 2 minus 1 over 8 there. Like so. Well, 2 minus 1 over 8, that's the same as 16 over 8 minus 1 over 8. We get 15 over 8 there. So 15 over 8 times by pi. We get 15 pi over 8 there. Okay. And there we have it. So that is V1 there. We now also need V2. So again, let's just do that in the same color here, just so you can see how this matches up. So for V2 then, what I've got here then is pretty much the same. The only thing that will change now is the integrand here. Okay, because we're integrating under a different curve here. We're now integrating underneath this curve here then, y equals 1 over 4x. So in that case then, we have, well, I forgot pi already. I can input it here though. So pi times by the integral then. Again, the limits are the same here. So 1 over 4 to 1. I've got y squared again. So y here is 1 over 4x. So we get 1 over 4x squared. 1 over 4x all squared here. And again, this is with respect to x here. So dx there. Okay. So we get pi times by the integral here. Again, the limits are the same. 1 over 4 to 1. So 1 over 4x all squared here. We get 1. Do it in brackets again. 1 over 16x squared here. Like so. And again, this is with respect to x here. Okay. So evaluating this integral here, again, just basic A-level maths integration. So what I get here then is pi times by. If we integrate this here then with respect to x, what we get then is minus 1 over 16x here. Okay. Don't forget the limits as well. 1 over 4 to 1 here. So all we need to do now is just substitute our limits in, just as we did here then for V1. I get pi times by. I got minus 1 over 16 times by 1. So I get minus 1 over 16. We then subtract the lower limit here. So if I substitute in 1 over 4 here, then what I get is minus 1 over 4. Okay. Like so here. Then if we simplify everything inside the brackets here, well, this is the same as minus 1 over 16 plus 1 over 4. So if we evaluate this here and times it by pi, what we get then is 3 pi over 16 here. Okay, so we get 3 pi over 16. So we're pretty much done here then. So we'll go back to the original pen color here then that we started this question in. So for the volume then of the shaded region R here, so that's V subscript R then, that is equal to V1 minus V2. So V1 minus V2 here. So in that case, then what do we get here? Well, V1, that was 15 pi over 8. So 15 pi over 8. We then subtract V2 here. So V2 is 3 pi over 16. So 3 pi over 16 here. So if we now get this over a common denominator here, then what I get is 30 pi over 16. 30 pi over 16 minus 3 pi over 16. Like so. And then if we evaluate this difference here, we get 27 pi over 16 as required. Okay, so as required there. And there we have it. That gives us the solution. Good stuff. So there we have it. That gives us the solution there to this example. And that brings the end then of this video here on adding and subtracting volumes.